Hey, everybody, we're going to get underway here. I want to make sure we have some time if you have specific questions you want me to address towards the end of class. So I want to make sure to touch on some main ideas along the way. And then if you have specific ones, specific either questions or topics, that we can have a little bit of time at the end of class to address that. So I'm talking about content pertaining to the third midterm exam, whether this is viewed as a preview or a review. My objective here is to try to serve as many students as I can. So I think whether you're struggling with quite a few of the ideas or there's just a few things that you need to improve on, I'm trying to serve both groups of students. So I come back to this idea that if I'm preparing for the test, if I'm a student here, I know a key thing is transforming the instructional material. You have information coming at you from so many directions. And as I've talked to students, a lot of you are doing a really good job of taking that and then summarizing it in a way that you find meaningful. Absolutely, that's a great strategy. You want to try to consolidate the information because that will help you identify what you think are the important learning objectives. You want to make it so it's not written in notes somewhere, but it's the way that you understand it and allows you to answer questions. So if you are able to do that, if you're able to take the information for chapters 7, 8, and 9, do those summaries then help you answer questions on the practice tests? If those are authentic questions and you've tried to summarize the information, that's a really great test to see, is that helping? Because what I suggest that you do is if it's not sufficient, if your summaries are not complete and not helping you answer questions, well, we can improve them. Having that as a resource, I think that's really essential. So what I want to do this evening, I'm going to step through the first practice test. I've organized it based on chapters 7, 8, and 9. Let's think about how that information would be summarized. And then I'm going to see if we can apply that for some new questions. So first of all, if I'm looking at chapter 7, and I'm trying to sort of organize and group the ideas together, what I found on the practice test was a question looking at when different elements were discovered. What they're trying to get at within this question is, well, some elements were known since ancient times. Copper would be an example. And the periodic table was put together, that's in the mid-1800s. That's before the discovery of the electron. It's not asking you, hey, tell me a specific year when element 116 was discovered. It's asking about these two different themes right here. There's a figure at the start of chapter 7. I know that that's what it's referring to. Next topic that we have within chapter 7 is the effective nuclear charge. So I see two patterns to that I'm able to explain. The dominant one is that the effective nuclear charge is increasing left to right because I'm not changing the shielding electrons, but I'm adding more and more protons. So that leads to increasing the effective nuclear charge as I move left to right. There's also a secondary trend, less important, but that's the one that's described here. It increases slightly as you move down a column. This right here is a statement straight out of the textbook. I know that's where it's getting it from, about how as you move down, the shielding becomes less effective. This is trying to think about explanations in chapter 7. Now, when it comes to effective nuclear charge, I'm really confident that these types of questions also appear. These types of questions meaning where you're being asked to calculate the effective nuclear charge, and that can be for any electron. It's not just the valence electron. Same equation for all of them. The effective nuclear charge would be the number of protons minus the shielding, where the shielding are the number of electrons that have a smaller principal quantum number. So if I were to calculate the effective nuclear charge, let's say for calcium, I could calculate the effective nuclear charge for, well, maybe one of its 1s electrons, it's 2p electron, it's 4s electron. You could pick any of the different electrons that calcium has and calculate an effective nuclear charge for it. For each of those, you take the number of protons, so I see 20 protons for calcium, and subtract the shielding electrons. So for a 1s electron, there are no shielding electrons. There are no electrons that have a smaller principal quantum number. So for those electrons, effective nuclear charge would be 20. If it's for a 2p electron, well, I have 2 electrons that are in a smaller principal quantum number, 1s2. So those would both be considered shielding. using this model right here, the effective nuclear charge would be 18. And then for the 4s electron, the valence one, it becomes +2. So easy calculation. We want to be able to calculate the effective nuclear charge for any electron in any of the atoms that we have. I'm grouping these whole set of ideas together. This is now when we're thinking about making ions. So we can be making our ions by either removing or adding electrons. So I see this being asked in different ways, and there's different things you have to look out for. So this first one right here is asking for the electron configuration of vanadium as a 3+ cation. Key idea there for making cations, when we're removing electrons, we remove them from the higher principal quantum number, and we have to be especially careful with transition metals. That's exactly what you see within this one. You notice the two main responses, students are able to remove electrons, but we're going to remove it from the 4s before we remove it from the 3d. The main error was removing it from the 3d rather than the 4s. Be careful with the transition metals. We remove it from the higher principal quantum number. When we're adding electrons, that refers to the electron affinity. This question's asking which, it gave multiple choice, but it was, what would be the reaction that corresponds to the second electron affinity of sulfur? So for electron affinity, we're looking at the atom in its gaseous state. We add an electron to make the anion. The second electron affinity would be taking now that anion, adding another electron to make it 2-. This would be the expression here for the second electron affinity of sulfur. Now, I got a polling question for you on this one. Would you think this question right here, I saw it on the practice test, do you consider that a fair question? The reason I'm asking is the textbook discusses successive ionization energy, and it shows us a few examples of those equations, but it never gives you an example listed for successive electron affinity. So I'm just curious, as a student, do you think that that's a fair question or not? So the way I'm asking it, successive ionization energy and successive electron affinity, they're similar. The book does not give you examples for both. Do you think it's a fair question or not? It's one that if I look back on the exam performance, students did pretty well. I'd put this in the category here of we want to be able to write equations for the successive electron affinity and also for the successive ionization energy. In some ways, it's just about knowing the format, I suppose. Looks like within this one, most folks are trending positive, saying, yeah, it's not necessarily that much of a reach. Fair, I guess we can't decide on fair. I know it's a typical question I might see. When I'm looking at then removing for the ionization energy, successive ionization energy, two thoughts there. The ionization energy always goes up as I remove the first, then the second, then the third. So the successive ionization energy is always increasing. And I see a very large increase. It increases a great deal when the electron's being removed from a much smaller ion. So if I'm looking at magnesium, I can remove one electron, I can remove a second electron, but then once I'm at the smaller magnesium 2+, which is isoelectronic with neon, it's going to be much more difficult to remove. So that's what I'm looking for within this graph right here. I could remove the first, I could remove the second, I'm seeing a slight increase, then a very large increase once I'm trying to remove the third one. So being able to understand and interpret data involving successive ionization, another learning objective. So if I'm summarizing this information, if I'm transforming the information, the instructional material, I probably have a summary on my page that brings together all of these. What does it mean to be making cations and anions, including successively? On that same topic right here, I think sort of part of that same summary are these features right here. So this is one where we're looking at ordering involving size, and the second is offering explanation involving ionization energy. So first of all, looking at an ordering based on size. They're considering carbon, fluorine, and silicon. So I show the ones right here. So instead of just coming up with the order, let's see if we can explain what's going on. As I'm moving left to right from carbon through fluorine, I am anticipating a contraction. It's getting smaller as I move left to right because I am in the same principal quantum number, n equals 2, but the effective nuclear charge is going up because I have more and more protons. So I'm thinking that I'm going to have a contraction as I move from carbon through fluorine, all the way getting smallest to neon. Then it gets much larger when I go to sodium because the principal quantum number is increased. And then I have a contraction as I move left to right from there. The reason I think that putting in order or being able to do ordering involving atoms, ions is so important is that's really closely linked then to the ionization energy. When the electrons are closer to the nucleus, it's smaller, it corresponds to a higher ionization energy. Now, this question right here, when I look at the ionization energy where data is given, this one's not asking me to make a prediction. It's giving data and it's asking why. So within this chapter, within chapter 7, you're going to have a combination. You have a combination of things where you're being asked to make predictions. Oftentimes they will be involving rankings, or data can be given and you're asked to come up with an explanation. So this one is asking about the relative ionization energy, that I sub 1 means the first ionization energy, and it's comparing sulfur and phosphorus. And it notes that, okay, between these two, the value for sulfur is a little bit smaller than the value that you have for the phosphorus. Now, in order to have this, let me send you a polling question on this. When it comes to phosphorus and sulfur, we didn't specifically compare those in class, but we did compare two elements that were somewhat unusual for the same reason that applies for these. Do you remember which elements we were talking about? We looked at general patterns of ionization energy, and we had a few anomalous ones, a few that didn't quite fit our usual pattern. Which of those, if you can recall, would have been similar to looking at phosphorus and sulfur? And when that's coming in, when I say it's unusual, I would have predicted what I said just a moment ago, that as I move left to right, the atoms are getting smaller, the effective nuclear charge is going up, and it's becoming a higher and higher ionization energy because the atoms are getting smaller and smaller. But this is saying, no, that isn't quite the case. There's something else going on within this one. Sharing results with you on that one, we're pretty much mixed as far as whether you can place the comparison that we're making or not. The comparison that we had right there was when we were looking at nitrogen and oxygen. When we were looking at nitrogen and oxygen, we saw that yes, they have positive ionization energies. Ionization energy is always positive, but it wasn't quite fitting the pattern between the two of those that we would have thought for the other elements within the P block there. And the same reason is what's being described right here. When we get to nitrogen, we're putting them in independently. And then when we get to oxygen, we have to begin to pair them up in the same atomic orbital. That will heighten the electron-electron repulsions, and it makes it a little bit easier to remove than you would have anticipated. Put this in the category that of offering explanations, in this case for ionization energy. Those ideas that I had right there, key ones for chapter 7, okay? The key ones, and when I say key ones, if you get these key ideas that I'm mentioning, you're gonna get at least 60% on the test, at least 60% to start from. Let's just double back to see the ones that I just mentioned that would have been key. We had one where it was very quick, just about tell me something about the periodic table. An explanation involving the effective nuclear charge, including calculations. Descriptions of making ions. Being careful when we're looking at our transition metals. Descriptions of the equations for electron affinity. And understanding and being able to explain and predict successive ionization. rankings involving size. It could be for neutral elements like this, neutral atoms. It could also be for ions. Offering explanations for things like the ionization energy, the electron affinity, trends in size. Right there, that's probably 3/4 of the questions that you'd experience, that you're going to that you could expect for chapter 7. If you can do those skills right there, you're going to do great on the stuff that we have from chapter 7. Let's do that for all of these. Let's see what can we do in order to reach about the, who knows, 60 to 80%, the core ideas. If I'm looking here in chapter 8, as far as core ideas and how I'm trying to make sense of it, first thought right here is we discuss aspects of ionic bonding. Aspects of ionic bonding, 2 different categories for that, 2 different skills. One was looking at aspects of the lattice energy, and one was looking at this Born-Haber cycle. Let's look at the lattice energy one first. So within this one, very typical format, which of the following has the largest lattice energy? So if I'm determining the lattice energy, first thing I'm going to do is look at the charge. The correct answer is calcium oxide, +2 and -2. Larger charges means larger lattice energy. I'm drawing your attention to calcium chloride. That isn't as large. That's +2, -1, -1. So when I say look at the charge, +2 and -2 has larger charge than +2, -1, -1. Okay. Look at the charges, larger lattice energy. Second, if I have ties, if they're both the same charges, then I'm going to look at the size. Smaller charges means smaller size. I want to adjust that one. Smaller size on that means the atoms can get closer together, and that leads to a larger lattice energy. Now, within the Born-Haber cycle one, a couple different questions on that. This one right here, as it's presented, this is the most difficult format. I saw it on this particular practice test. If I had to guess, this is more difficult than you'd have to do. I'm sure you have a question about the Born-Haber cycle. This is the most difficult one, the lowest scoring, because it's asking you to calculate something, but it doesn't give you the framework to put together the parts. Let me show you how it comes together. This is looking at the lattice energy for the potassium bromide. Made a quick sketch of it. This is what I would expect within the Born-Haber cycle to have. Way at the bottom is the ionic compound that we're interested in. The step above that, most immediately above it, these are the elements in their standard state that you find in the standard enthalpy of formation reaction. You need potassium and 1/2 of Br2, which turns out to be a liquid. Then the rest of my trajectory here, I need to get to the ions. I need to get to the ions that would be the potassium plus and the bromide minus. So what do I need to do? I need to take it from the solid to the gas for the potassium. I'm going to take the anion, the Br2 from the liquid to a gas. Sorry about that. So I have the gases for both of them. I'm going to break the bond and go from Br2 to just get Br atoms. We'll make the cation. We'll add an electron to make the anion, and then that final portion, that's the missing step. The way I solved this, I made that sketch and then I added in the features. This would be corresponding to the standard enthalpy of formation. This would be going from the solid to the gas for the potassium. When I'm breaking the bond or I'm transforming from the Br2 liquid to the Br2 gas, just got to be careful there because that was listed per mole, but I only have 1/2 of a mole. So I cut that value in 1/2. When I was breaking the bond in Br2, I cut that value in 1/2. I am making the anion, or I'm making the cation with the ionization energy, and then I get some of the energy back when it comes to the electron affinity. Like I said, this is the most difficult version of this question because you got to put together the framework first and then see where the different values fall. I noticed on the other practice test, the questions were set up. If it was on the same topic, they were easier to do. The reason we're doing any of this, the one that you can't experimentally get, the reason we're going all the way around this is in order to get this missing step right here, which is the lattice energy. So when it comes to then start of chapter 8, ionic bonding, 2 different topics. The easier one, I think, is probably the one involving lattice energy, where we're looking at charge and then we're looking at size. The somewhat more involved one, but I think you can do it, are aspects of the Bohr-Haber cycle. This one right here that I'm grouping together, these are all what I would put in the category of being able to draw and evaluate Lewis structures. Different ways it's being asked, but I think it's all exactly the same skill. Drawing and evaluating Lewis structures. So my features that I'm looking for within this one, if I'm being asked, say, which of these is the dominant structure or the best Lewis structure? I know to students, a lot of times it seems like, well, you're just sort of guessing. How did you come up with the best one? This is what I'm looking for. For elements like carbon, nitrogen, oxygen, fluorine, I'm expecting them to be octets. I know that hydrogen is only going to be in a single bond. Turned out fluorine's also only going to be in single bonds. So if I'm starting with things that I absolutely know, that's what I'm starting out as far as criteria to have. A secondary factor, and many times it's going to show up in these, is being able to calculate and use the formal charge. Recall the way that we calculate it? It's the number of valence electrons minus half the number that are found in bonds minus the number of lone pairs that it has. The more formal charges that you can have closer to 0, the better. If you have to have non-zero ones, we prefer to put negative formal charges on the more electronegative atom. This is the plan that I'm using when I'm evaluating all of these. So the way it comes together, if I look within here on the bottom right, this would be an example where I have octets or hydrogen with just a single bond. And I also have formal charges of 0 for the nitrogen and the oxygen. So that's a great structure right there. That's definitely the one that I would choose both on octets and formal charges. If I look up here at the one on the top left, I know that the formal charges can't all be 0 because the formal charges add up to the overall charge. The overall charge is -1. So I'm going to have to now figure out, well, how do I choose the best one based on formal charge? Quick thought here on electronegativity. We said that fluorine is the most electronegative atom. The second most electronegative groupings are immediately to the left and immediately below it. So if I look within this one, I think nitrogen is more electronegative than sulfur. I'm sure it is within here. But then when I'm looking to do my analysis, I'm going to first see what are the formal charges in each. So first of all, the formal charges, they always add up to the overall charge. -1, 0, 0, -1, +1, -1, 0, +1, -2, +1, 0, -2. So these are all the formal charges that I assign. So within here, before I ask, well, let me put the negative on the more electronegative atom, I'm going to say, do I have a case where they're all closer to 0? I absolutely do. I have a case where they're all closer to 0. That's what wins in this setup right here. So if we're trying to look at our criteria again, we want to be having octets, formal charge. We're first seeing that it's better to have as many as we can close to 0. And then finally, if we then have, if you want to say another tie, if we have to somehow have negative charges somewhere within that, I would put it on the more electronegative atom. But out of my group here, I think that's the best choice. The one at the top right here, I think this is also about the Lewis structure. What's being known to exist? It's asking, which of these can you have be hypervalent? Sulfur, we saw from our second row on down. We can have hypervalent, we can exceed octets. That's fine for SF4. All of these I'm grouping in the same category skill-wise, drawing Lewis structures and evaluating them, including formal charge. This group right here, I'm also putting all 3 of these in the same category. All 3 of these are the same skill, all involve the same skill, which is accounting for resonance structures. Let me show you about that. So this one here on the top left, It gives some bond enthalpy data for an oxygen-oxygen single bond and an oxygen-oxygen double bond. And it's asking, well, what would you predict for O3, for ozone? Ozone's a classic example they're trying to use of saying that you have resonance there. If you draw the structure for resonance, or the Lewis structure, you find that you could have had the double bond on the left side or the double bond on the right side. Where is it? Is it on the left or the right? It's on both. You do not actually have a double bond and a single bond. You have an averaging of these two structures. A single Lewis structure is not sufficient to describe the bonding that you have in ozone. You need a combination and averaging of both of those. That averaging, we said, affected the bond order, the bond length, the bond strength. Instead of having a single bond and a double bond, you got an average. It's somewhere in between those two values. That's what it's getting at with this question. The idea of saying that you have an averaging of the environment, that's what's also taking place with this question on the top right. If you look within that, and they're showing the arrows, you've got multiple resonance structures. And it's asking about that in different ways. The correct description for what's going on, it says all of the bond lengths are equal. Now, if you say, how can they be equal? I see double bonds and single bonds. And I would say with resonance, we do not have double bonds or single bonds. We've averaged all of those structures that we have together. The idea that they're trying to get at here is that when you have resonance, you no longer have double bonds and single bonds. You've got an averaging of those environments. A single Lewis structure is not describing what's going on. It is not the case of the double bond jumping back and forth really quickly. You've got a combination of the double and the single. That's why we would describe this as a bond order of about 1.5 between the oxygen and oxygen atoms. That idea of being able to determine the bond order, that's what I need for this one over here on the bottom left. Here, we're asked to compare aspects of bond length for these 3 different ions. Here are the different ones. I have the Lewis structures for these. Take a second, see if you can look at each of these and determine what is the nitrogen to oxygen bond order. We're being asked to compare the length. I think we first have to think about what is the Lewis structure. If we have resonance present, what would be a good way of describing that nitrogen-oxygen bond order? And we will use that to determine the bond length. Take a second, see if you can look at what I have right here, and we'll move on from there. If I were to look at these features right here, and the very top one, I see a double bond. In the one down, I see a single bond and a double bond, but I could easily have resonance and flip those back and forth. So I think this is not a sufficient Lewis structure. I think I have an averaging of the environment. Same thing with the bottom one. I think I have an averaging of the environment there. I think that I end up within my setup of seeing a double bond, a fractional bond of 1.5, and a fractional bond that's below that. That's what I would then be using when I'm trying to then think about aspects of bond length, bond strength, bond enthalpy. Let me ask you on this one. When it comes to then doing Lewis structures, the skill is being able to draw it, interpret it, apply formal charge, and think about resonance. Where do you self-assess on this one? Is this something you think you can definitely do, or something that you don't have much of a chance on? If I had to pick a single idea from chapter 4 that's going to be important, it's exactly this. Drawing and evaluating Lewis structures, calculating the formal charge, accounting for resonance, and connecting it to things like bond length, bond strength, bond enthalpy. And the reason I say that that's a crucial one is I see within here, so we're we're trending 4 or 5. I think that's a good sign right there. The reason that that's so important is look at these different examples. This one was involving accounting for resonance. These are all on the same practice test. This is doing a ranking involving bond length, bond strength. Here was one where we are accounting for resonance. There was one about exceeding octets. There was one about assigning formal charge and evaluating it. There was one about looking for octets in the formal charge again. So right there, 1, 2, 3, 4, 5, 6, at least 6 questions within chapter 8. They're all on the same skill. Really important one. And as we know, that's a skill we also need in chapter 9. Another set of skills that I put together, these are coming at the same idea, but in different ways. This has to do with looking at a particular bond and talking about whether it's covalent, polar covalent, or more ionic. This one on the left right here, this is saying of these elements, which of these has the most polar covalent bond when it's bonded to hydrogen? So within here, I'm thinking about a particular bond that I'm comparing, something bonded to hydrogen. And I have different choices right here. So first thought is, we got to be clear, what does it mean when it says polar covalent? I'm thinking of a continuum of something that can be quite ionic, where I have cations and anions, all the way to being purely covalent, where it's the same atoms in the bond. And along that continuum is where I find polar covalent. It becomes more and more polar covalent when I have differences in electronegativity. It becomes more and more purely covalent when the electronegativity values get closer and closer together. So we want to make sure that's what the vocabulary is asking. The most covalent I'm reading as the largest difference in electronegativity. So it comes back to fluorine's my most electronegative. The second tier would be nitrogen and oxygen, and chlorine and bromine. The placement of hydrogen, we have to be careful. It's a little bit left of carbon within this. So if I'm saying combining hydrogen with carbon, that's going to be pretty close to a covalent bond. It will still be polar covalent, but it will be pretty close to this covalent one because they would be quite close in electronegativity. When hydrogen is with hydrogen, I'm sure it's a covalent bond. When hydrogen is with phosphorus, I think that's a polar covalent, but it's even more polar covalent when it is with something that is more electronegative, like the chlorine. That's how I'm using this. If you have a periodic table that you can use on your test, which you do, you might want to add this notation here to yourself to better understand the relative electronegativity values and how you would use them. This next one right here, this is talking about a diatomic molecule and its dipole moment. The dipole moment, what factors influence that? The way this one's being asked, it's which of these contributes to a larger dipole moment? And it says both of these are true. Well, first of all, let's see if we can make sense about how both of these being true. Bromine is larger than chlorine. Okay, I buy that because it's a larger principal quantum number, same column. Yep, bromine is going to be larger than chlorine. In terms of the electronegativity, bromine is less electronegative than chlorine. Yep, I buy that too. It's becoming more and more electronegative as I move towards fluorine. So how does this then contribute to the dipole moment that I have? I don't think you're going to be asked, I know you won't be asked to do this calculation, but we need to know what variables affect the dipole moment. The dipole moment has to do with the distance the charges are apart from each other and how positive and negative they are. A larger dipole moment corresponds to when the charges are farther apart and when you have it be in even more polar covalent, even more positive and negative. So if you look within both of these, how does it begin to explain then the dipole moment value that you have being larger for BRF? Well, we see that because bromine is larger, the charges are farther apart from each other. Yep, that's a factor that contributes to the dipole moment. I also have a greater difference in electronegativity between bromine and fluorine. That makes the charges even more partially positive and partially negative. That's how both of these are contributing. This one, I would say, again, it's not a calculation, but it's understanding the factors that are leading to the dipole moment. Another topic that we have there within chapter 8 was interpreting these energy well diagrams. This one says this dashed line corresponds to a carbon-carbon single bond. And now it's saying, which of these could correspond to a carbon-carbon double? So my analysis within this one, what am I thinking? I'm thinking that a double bond, it's a shorter bond than a single bond. It has a deeper potential energy well. It has a higher bond enthalpy. Those are the comparisons that I'm making here. So I'm thinking about how things connect, like a single bond, a double bond, and a triple bond with aspects of the bond enthalpy, the bond length, the bond strength. That's what this question is after here. One that I saw within that test, that was an idea that we haven't quite had yet, that's at the end of chapter 8, is this question right here. So it says, how many delocalized pi electrons would be present in acetic acid? How many in acetate? Let me add some information for us here. So first of all, this would be a Lewis structure for acetic acid. If I look at this, I don't see any resonance taking place. I see that I've got a double bond with this oxygen, a single bond, a single bond. It's not the case where I can just flip where the electrons are and make an equivalent structure. I don't think I have any resonance taking place here with acetic acid. With acetate, it's different. Here is a Lewis structure for acetate. This one's drawn with the double bond pointed up. You could have just as easily drawn it with a double bond pointed to the side. You've got two different resonance structures here. What is the environment like in the acetate? Well, it's a combination of these. You don't have a double bond and a single bond. You've got that extra bond, if you want to think about it that way, between both of these oxygen atoms at the same time. It's leading to a fractional bond order. Say it's a bond order of 1.5. Those electrons, instead of being found in a double bond just with one atom, they're smeared out. They're a combination between both of these. They are delocalized. They are not a localized double bond, which is just in one region. They're spread out due to resonance across this broader region right here. The two electrons that in this Lewis structure are being shown in a double bond are actually spread out in this entire region right here. So a takeaway within this one, delocalized, that's another way of describing the resonance. You have resonance structures to account for the fact that the electrons are delocalized. So in a way, all this question's doing right here is adding a description of saying, which of these has resonance? Is it acetic acid, acetate, both, or neither? That's what the point is right here. I would say you do not have any delocalized electrons in the acetic acid, and you've got two delocalized electrons that, instead of being found in a pi bond there, are spread out through that region. I'm not sure this is going to be a topic that you'll have on your test. That's why I sort of left it as an afterthought, but this is definitely an important idea that you find in organic chemistry. Moving on then to ideas that I think are crucial or important in chapter 9, 3 big sets of topics: VSEPR, valence bond theory, and molecular orbital theory. Here I summarize different aspects of what we want to be able to do when it comes to the VSEPR predicted geometries. For all of these right here, if I'm summarizing it, I want to be able to draw a Lewis structure, know what the VSEPR predicted electron domain geometry is and molecular geometry, consider the ideal geometry, what would be the corresponding bond angles, and then consider, are there distortions from that ideal geometry, and what is the polarity of the molecule? If I'm looking within the different features within here for how folks were doing on it, if I look at this top left one right here, the question is asking about the bond angles that I have in BH3 or the bond angles that I have in this case where I have 2 hydrogen, a carbon, and an oxygen. BH3, I would say, is my ideal trigonal planar. I think all of those angles are 120, 120, 120. In the one where I have a double bond, the way I conceptualize it would be, okay, I'm going to first mentally think about them all being 120. And then I'm going to say that this double bond takes up more space. It's going to squish this hydrogen carbon hydrogen angle a little bit smaller than 120. And these other two opposite it, those will both become a little bit larger than 120. So if I'm thinking right here, which of these ends up being the smallest? It's hydrogen carbon hydrogen, because the double bond on the opposite side is taking up more space and it's compressing that angle a little bit. Notice within the setup on the format, it doesn't say, tell me precisely what that angle is. I think that this was well written where it's asking you to do a comparison, but you don't have to say precisely what that particular angle value is. If I look within the second one here at the bottom, identify the molecule with the largest dipole moment. I need to evaluate based on the molecule, do I have the different bond dipoles canceling due to their symmetry and gives me a dipole moment of 0? Or is it a polar molecule that still has a dipole moment? So first of all, in terms of the vocabulary right there, something that is a polar molecule has a dipole moment. Something that is a non-polar molecule has a dipole moment of 0. I've seen some questions where it says a non-zero dipole moment. They mean a polar molecule. Non-zero dipole moment means it has a dipole moment. It's a positive number. It's a polar molecule. If I looked within the choices right here, I only see one polar molecule. BF3, well, is this trigonal plane. It would be a trigonal planar environment. When you have a trigonal planar, the triangle, if that was boron with fluorines all on the outside, dipole moment there ends up canceling. And the net then is a nonpolar molecule. CF4, that's tetrahedral, they cancel. Silicon H4, tetrahedral, they cancel. The only polar molecule that I see here, the one that has a dipole moment at all, is IF3. Here I show then what the Lewis structure would be for that. This would be a T-shaped. The way that I think about this geometry is the electron domain geometry. This would be a trigonal bipyramid, pyramid on the top, pyramid on the bottom. I've added lone pairs that went then equatorially. That's the triangle in the center. In this then overall molecule, the dipole moments do not cancel. This would have a dipole moment. This would be a polar molecule. This idea here at the top identified the pair with the same molecular geometry. I think that this is the same plan. Tell me the Lewis structure to get the VSEPR predicted geometry. And then in this case, describe what it is. Both ammonium, NH4+, and CH4, they're both tetrahedral. All of these are in the category here of working with VSEPR. All of these are in the category of valence bond theory. So this one over here on the top left, identify the hybridization as you move left to right within this. In order to determine the hybridization, I'm going to look at the electron domain geometry. I don't have any lone pairs on these, so I can simply look and say, okay, I see a trigonal planar, I see linear, I see trigonal planar. Those are the electron domain geometry, so that tells me this is sp2, sp, and sp2. If I were to take this another step and say, how would I describe the bonding in this? Let me explain how I think each of the bonds are formed. Beginning with this carbon atom on the far left. I think that carbon atom on the far left is sp2 hybridized. That means I have 3 different sp2 hybrid orbitals. One of them is pointed to the hydrogen. It overlaps with the 1s of hydrogen and makes a sigma bond. One of those sp2 is pointed at the other hydrogen. It forms a sigma bond with the 1s for that one. When I look between the 2 carbon atoms, I see a sigma bond present. That was being formed from the sp2 hybridized orbital and the sp hybridized orbital. Sigma bonds are being formed by that carbon on the far left. It's hybridized orbitals. Sp2 tells me it has one p orbital that is left over. One p orbital that is left over and unhybridized. It is perpendicular to that plane. It is perpendicular to the plane of the sp2 hybridized orbitals. It is off of that axis, and that is what's leading to this carbon-carbon double bond. That's what is contributing to that. So what I'm trying to do within this, two different skills. One is I want to identify the hybridization, and then I want to be able to use that to describe how the bonds are being formed. This one on the top right, how many sigma bonds are formed? I think what you have to do with that, draw out the Lewis structure and then just count them up. When we count them up, each of our single lines is a sigma bond. When we have a double bond, the first line is a sigma and the second is a pi. That's why we add them up within that. This bottom left one right here, I was getting some really good questions about this. It's asking which of the molecules here are planar. Let me add some information and show you what they're talking about on that question. So first of all, here are the Lewis structures for each. The N2H2, this would be the Lewis structure. Crucially, notice it's got a lone pair right there on each of the nitrogen atoms. And in ethane, C2H6, this would be the Lewis structure there. So take a second, look in the C2H6 for that carbon atom. How would valence bond theory describe the bonding there? How would you use valence bond theory to describe the bonding in C2H6? Do you need hybridization? If you do, how is that set up? Take a second, see if you can think through how is valence bond theory describing the bonding in C2H6? If I were to look at that, I would say each of those carbon atoms are sp3. Each of those carbon atoms have a tetrahedral electron domain geometry. The bonds are being formed between those sp3 hybridized orbitals in the 1s, the 1s, the 1s, and an sp3 overlapping with another sp3 on the other carbon. That's how I'm envisioning what's taking place here. One tetrahedral stuck onto another tetrahedral. How about in this case right here? Look at those nitrogen atoms. How would you describe the bonding there? How does valence bond theory describe the bonding in this N2H2? If I look at those nitrogen atoms, each of those are sp2. Each of those nitrogen atoms, I see 3 electron domains. One is headed towards a bond with hydrogen. One is a lone pair, and the other electron domain is towards the other nitrogen. 3 electron domains means it's sp2. So now notice how I would use this to describe the bonding. In those sp2 hybridized orbitals, all 3 of those hybridized orbitals are in the same plane. They're a triangle. One of them is forming a sigma bond with hydrogen. One of them is holding a lone pair. One of them is forming a sigma bond with the nitrogen. I have a triangle there with these sp2 hybridized orbitals forming a sigma, and a lone pair. That's what the sp2 are contributing to. Are you with me that I would then have a leftover unhybridized p orbital on the nitrogen that's perpendicular to that plane that could form a pi bond with the other nitrogen atom? What ends up happening is it forces this to be a planar molecule. All of these atoms are within exactly the same plane. As if you had a piece of paper, all of these are being constrained to be exactly in the same plane, because that's the only way this double bond can fit together. The double bond must be coming in and out of the plane for this nitrogen, in and out of the plane for that nitrogen. That's the only way those p orbitals can overlap. The overall geometry of the molecule is being constrained. It's being held in place by the need to have the p orbitals overlap to form this double bond. That's what it means to say they are planar. That's pretty high-end application and implication for where valence bond theory leads us. This is, again, back in the category of definitely an idea that you see a lot in organic chemistry. How are molecules either free to rotate, like we have with our tetrahedral single bonds, or are they constrained and stuck together and unable to rotate, like we see with this N2H2? I intentionally left this idea sort of off our to-do list as we went along. I think it's probably a pretty advanced idea for our tests that we have. I think our initial ideas and skills of using valence bond theory to describe the bonding that's taking place, determine whether it's hybridized or not, I think that's pretty much mainstream for where we need to be. The last set of ideas that we had there pertaining to chapter 9, they were being able to characterize different molecular orbitals using designation as pi or sigma, bonding or anti-bonding, and then being able to populate provided energy diagrams. The last skill that's not being shown here is to consider where do these molecular orbitals show up then on the diagram. I would say within this case, I have anti-bonding that was being formed by p orbital with another p orbital. In this particular figure, it would show up here. I have anti-bonding with a p orbital with another p orbital. I place that here. This one looks like it's a p orbital with another p orbital forming a bonding, but they're along the same plane, or the same axis. And this one looks like it's anti-bonding of an s orbital with another s orbital. That's how I'm seeking to identify where these would be then found within the diagram. It looks like as I'm using the diagram, I see two different skills. One is talking about bond length, and one is talking about the magnetic properties. In both cases, you just take the correct number of electrons, fill them up. I show what would be taking place here for this C2. If it's a cation, I would be removing electrons. If it's an anion, I'd be adding them. So both of these, it seemed like at least initially, students were doing pretty well on. These would be then the last aspects from chapter 9. So what I want to do within here, I want to take these same ideas and skills that we've just mentioned and see how they showed up on this other practice test. If the ideas and skills that I just mentioned for chapter 7, 8, and 9, if those are the kinds of things that you can summarize and make a plan of and be able to get correct, let's see how well that would take you on to practice test 3. Let's see if the same ideas and skills appear. So within chapter 7, okay, I see a question about what would have been on Mendeleev's periodic table. Silver, okay, that's one that's known since ancient times. That would have been on the table. Effective nuclear charge, I want to be able to do calculations involving effective nuclear charge. This is showing me data for the inner electrons and then for the outer electrons. Notice for the outer electrons, it's a periodic trend. It goes up and then it comes back down, and it goes up and it's going to come back down. But not so for the inner electrons, because for the inner electrons, we never have any shielding electrons. As the number of protons goes up, the effective nuclear charge goes up. Whole group of ones here back to chapter 7 of making sense of ionization energy, size, electron affinity. I see within this grouping right here, which of these has the strongest influence on the first ionization energy? It matches up really well with the size. How about the largest ionization energy in this group? I'm looking for something that's quite small. Beryllium 2+, that's not something I've memorized, but look at beryllium. If it loses one electron, another electron, it's down to just having one s electron, 2 of those, and 4 charges plus 4 protons. That's going to be really small. Which of these has the largest ionization energy? I'm sure it's the beryllium 2+, because that's definitely the smallest. This one here on the top right, this is looking at placing a combination of neutral atoms and ions in order. Again, I'm thinking about these in terms of the factors that are affecting the size. I see questions involving successive ionization. One on the top left is, do we know the formula? The one on the right, this is just another way of asking what was on the first practice test. It's even the same element, magnesium. I see that I have a steady increase. I can remove one electron, second electron, it goes up. It goes way up when I'm now removing from the smaller ion, the one that is now isoelectronic with neon. How about this one right here? This is electron affinity, and we're being asked to explain it. This is back into the category where it gives me data, and it's now asking, how would I explain it? It's more favorable to add an electron to chlorine than it is to fluorine. Before I would answer this one, as much as possible, I would pause and say, okay, what is the explanation in my head? Because as I start to read these things, more and more might sound convincing. What might contribute to make it more favorable to add an electron? Well, I know I don't want to add an electron to an orbital that already has an electron. I don't have a choice in this. Both fluorine and chlorine, I have to add an electron to an orbital that already has an electron. But it's going to be a little bit easier to add it to one that is larger. A larger orbital for chlorine rather than the fluorine, that's what makes it a little bit easier. That's what we're trying to get at within that one. Chapter 8, key ideas. We said that we need to know aspects of ionic bonding. This one's involving lattice energy. This is now looking at the smallest lattice energy. I'm first looking at charge. I see I have a +2 and -2, +3 and -3, +2, -1, -1. I only have one example of +1 and -1, so lithium fluoride must be the answer on that. Standard enthalpy of formations being asked, given the information that we have within the Born-Haber cycle. This is the case of it has information about all the different legs except the missing one right here. And then doing the corresponding calculation for that. However you want to get to it, meaning you have to go up and then come back down, and then this would be the missing value. That's one way that you could do it. It's, again, remember, this is just an application of enthalpy being a state function. Pathway doesn't matter. Which bond exhibits the most covalent character? In order to answer this, I'm thinking back to the electronegativity. Carbon and hydrogen, really close in electronegativity, which means it's much closer to being a covalent bond. That's what it means when it says the most covalent character. Here I see a host of ones involved in Lewis structures. Which of these is the dominant Lewis structure? Which of these violates the octet rule? Tell me about the formal charge. I'm going to come back to that strategy of first look for octets. Then I'm going to say I want formal charges as much as I can close to 0. And then if I have a couple that have that same scenario close to 0, I'm going to put the negative on the more electronegative. That's the criteria that I'm looking at when I'm trying to answer that one right there. As far as violating the octet rule, nitrogen and oxygen, it turns out that does violate the octet rule because you have an odd number of electrons. There's no way that you can have the octet rule if you have an odd number of electrons. SF2, in that case, I would be drawing the Lewis structure for that, and you'd find in that case that's consistent with the octet rule. Within this last one, it's asking about, tell me about the formal charge. There's a couple that I noticed that had that skill of giving you the connectivity, but it did not include the final aspects of the lone pairs. You got to read it carefully. It says fill in the missing lone pairs. So how would I end up adding that? Adding those lone pairs, I've got a total of 6 more electrons I need to add. This idea of adding 2 to the oxygen and 1 for the sulfur. That's giving me an octet around the oxygen. I'm exceeding for sulfur, but that's no big deal. Sulfur is an element that I can exceed octets for. And then I'm calculating the formal charge on that. Formal charge is 0, and in fact, formal charge is of 0 all the way up throughout. That's how I do that one. This one right here, this was one that wasn't really too much on the first practice test. So let's consider this as far as adding a new idea for us. So the one on the left-hand side, this is something that we practiced, I want to say back in chapter 5, where we used provided bond enthalpy data. And we considered whether the overall enthalpy change was endothermic or exothermic. The way I solved that one, well, first of all, the reason that this is in this chapter and not in the previous chapter with quite the same format, it now gives the formulas. It is not showing the actual structure. When we did this back in chapter 5, it would show you a picture and you could look and say, okay, do I have double bonds? Do I have single bonds? Let me now consult the table. The reason this one's showing up now is we think that you can draw this. We think you can draw CH3Cl. We think you can draw the different molecules here. But then the plan is still the same. It's going to take energy in order to break the bonds. It's always endothermic to break the bonds. You can add up all of those contributions. That's going to be a positive number. You can subtract all of the values that you have for forming the bonds, because that's going to be exothermic. Bond forming is always exothermic. That's what you then use to determine whether the overall process is endothermic or exothermic and how much. And again, the reason it's showing up here again, we think you can draw the molecules now. And back in chapter 5, they had to be given to you. Take a second, we'll send you a polling question on this one. So this one has the bond enthalpy for carbon and hydrogen has a value. For carbon and bromine, different value. And the question is, which of the reactions is most exothermic? And it gives 4 different examples. The way I want to phrase this one here is, when you have this bond enthalpy data and you're thinking about things as being endothermic or exothermic, do you have a plan? Do you know what this question's asking? Would you be able to answer that, or you're not sure what even to look for? As I look at that, I mean, the bond enthalpy is a reflection of the strength of the bond. I'm thinking how bond enthalpy relates to the depth of these energy well diagrams. When I have those energy well diagrams showing how the bond energetics, the depth of that well, the depth of that well tells me how much energy it would take to break the bond. And the depth of that well is also telling me the energy I get when the bond is being formed. Bond enthalpy values, remember, we can think about them both ways. When it's viewed as a positive endothermic value, that's the value it takes to break a bond. If we think about that same magnitude, but as a negative value, that's how exothermic it would be in order to form the bond. That's why I'm taking it back to what those energy well diagrams look like. So if I'm looking at this one, it's asking me, what kind of reaction would be most exothermic? So right away, I see, looks like they're setting it up with 2 variations. They're saying, start with the molecule and break it apart to be the atoms. Start with the molecule, break it apart to be the atoms. Or start with the atoms separate and have them come together to form the molecule. If it's asking me for exothermic, it's got to be forming the bonds in the molecule. Bond forming is always exothermic. Bond breaking is always endothermic. So these first 2 examples, when I'm breaking apart carbon with 4 bromine bonds, carbon with 4 hydrogen bonds, if I'm breaking those apart into the atoms themselves as these gaseous atoms, both of those have to be endothermic. Bond breaking is always endothermic. So now I just got 2 choices. These ones at the bottom right here, these are both exothermic examples. If I now look at the data, okay, CH4, that's going to be much more exothermic. It's coming together to form stronger bonds, bonds with a lower potential energy, bonds with a larger bond enthalpy. I'm looking at the data, and that's how I'm agreeing with this one. I'm deciding that the CH4, the formation of that from the atoms as they're just separate, that's going to be the most exothermic. So my plan on this is twofold. I'm first of all saying, if it's exothermic, I have to be forming bonds. And secondly is it more exothermic than another one? That point, I'm looking at the data. That would be my strategy for solving that. This one right here, I give you two examples. Take a second, read both of those. In either of these cases, just based on how it's asked right here, what do you think, would they involve resonance? Is resonance something that you're looking for there? Does the top one, does the bottom one, do both of them or neither? As I see those come in, if I read them, so the bottom says, which species requires resonance to explain the fact that all the bond lengths are equal? So that bottom one, that definitely seems it's a question involving resonance. It's saying that if you consider the Lewis structure and the resonance present, which of these leads to an averaging of the bond order that would make it so all of the bond lengths are equal? If I'm thinking about something like NH4 plus or NF3 minus, I can draw Lewis structures for those. I think the bond lengths are equal to each other in NF3. I think they are equal to each other in NH4 plus, but I don't need resonance to explain that. That's what we're getting at within that one. So I think that that bottom one there definitely involves resonance. I agree with folks that are saying that. If I look more closely, I think the top one also involves consideration of resonance. Really classic question. This was set up similar to on the first practice test. It's asking about the carbon-oxygen bonds that I would have in these different molecules or polyatomic ions. And it's asking about the bond length. So what I need to do is I need to draw the Lewis structure, look at the bond order, and I need to potentially think about resonance. And you know what? I'm sure that the carbonate there, CO3 2 minus, is going to have a fractional bond order due to resonance. Really common to have that present in these types of questions. So in this case, both of these, I need to consider how resonance would be important. Chapter 9, 3 sets of skills again. A lot going on, but they can all be grouped together. All of these have to do with VSEPR, whether we're looking at the shape, describing whether it's a polar molecule or not, looking at bond angles. Notice within the screen, 1, 2, 3, 4, 5 different questions on that practice test, all had to do with VSEPR. Great skill that we know we can master and that we're going to get a lot of questions right if we can do that. Valence bond theory, I saw a couple of those. Within these, we're asked to then assign what would be the hybridization and how the bonds were being formed. In molecular orbital theory, I see the same set of 3 skills. I see ones where we have to populate the diagrams. I see ones where we have to interpret the image. And I see ones where we have to place the image on the diagram. Those are the 3 different skills that we're up to. I also noticed when I looked within these, folks are doing pretty well, I think, on the ideas from chapter 9, because I think that they're the most recent that we've had. I know they're the most recent. And so if I would say, if I were to double back and say, what ideas do I need to get from the earlier chapters? Absolutely the Lewis structures, because that's a big part of chapter 8. And it's a precursor that we need in order to do well with like our VSEPR predicted ones. Now, when I said, how were these ideas showing up on the 3rd practice test? The ones that I quickly went over here that would have been on my study sheet, they were more than 80% of that test. Okay, they were like 82% of the questions were just this last set that I quickly went over. Now, I know I went over them quickly. I'm not saying that, oh, these are all easy questions, but I'm saying they're all topics and questions that I think we could predict are going to be on the exam. If we can predict the types of questions that are going to be on the exam, if we can practice them ahead of time, and that ends up being 80% of the test, we are in really good shape to being able to say, yes, we can master those ideas. Okay, so I'm saying that even though we have a lot of different ideas across chapters, I think that we can get our handle on them. Now, as I've shared information with you, I know that this really depends on how familiar you are with the ideas already. So let me ask you this question, polling question. With the stuff that I talked about tonight, was it stuff that it wasn't really a good match for your understanding because it was too advanced? Or maybe it was things that you already knew how to do, or somewhere in between? As those are coming in, a couple different suggestions for you. If the stuff that I talked about were things that you already mastered and you thought you were in really good shape on, that tells me that you only have a few stray ideas that you might come across, that you might want my feedback on. For the most part, you're good to go, but you might find some strange idea here or there. If you thought that you've mastered most of these, if you come across a strange idea in the next 24 hours leading up to your test, let me know, okay? Send it to me and I think I can help you out. Within the group right here, I don't have anybody saying, yeah, these were things you already mastered. If I look at this other one, point one, as far as saying these were far beyond your current understanding, very few folks are commenting on that either. That's great, because that tells me a lot of the things that we talked about, you either have a decent understanding of, you have some understanding, and the feedback is going to help you. If you're in this middle zone, 2, 3, and 4, where most of the folks are, I think we are in a really good shape to be able to finalize any of the ideas here and get ready for the exam. You're at the point where any feedback that we offer, you're ready for it, okay? If we would have started 2.5 weeks ago and I told you about, well, you know, in a VESPER predicted geometry, the lone pair is going to take up more space as an electron domain geometry, you would have just shut me off. You'd say, Clark, what the hell are you talking about? But now you get that. You have so many of the parts together. Let's just take those and turn them in to the understanding that will allow you to get the questions right on the test. And I know you can do that, okay? Let me ask one more question within here. So based on what we talked about, this one, multiple, check all that apply. Where do you feel about your confidence for the test? Do you think we addressed one or more weaknesses you might have had? Do you think you know the key ideas that we're going to expect on the test? And then tell me, do you think you're going to transform the instructional material? I'm just curious within this. If it's me right there as a student, I really want to be able to check those third and fourth. I want to know what the expectations are, the types of problems to expect, the types of skills to expect, and then I want to do the very best I can to transform the ideas and make sure I get them right. Make sure I get them right. I think back to my own experience. So as an undergrad, I was a triple major. One of my majors was history, one of my majors was chemistry, one of my majors was religious studies. In 2 of those classes, history and religious studies, they were not multiple choice tests. You would show up to take the test and they would say, okay, we're going to have 4 essay questions, something like that. We'll tell you what they are ahead of time. So it'd be ridiculous to show up and say, well, I'm going to start thinking about it as soon as I get there. No, if you have a good sense of what's there, what I would do is I'd outline it. I would take all the information for what I've been reading. I wouldn't write the whole thing, but I would give myself, okay, I think I'm probably going to touch on these 3 key points. And so I'd get them all clear in my head the best that I could. So when I showed up on the test, it was just trying to reproduce that information. And I found the same thing worked for my chemistry exams. The same thing worked for my physics exams. Those were not essays, but if I could take the ideas and consolidate them and put them on one piece of paper for a given chapter, all I needed to know then was what was on my piece of paper. And if my piece of paper wasn't good enough, it didn't help me in my homework, it didn't help me with my practice exams, I would just improve it. I think right now, let's see if we can do that. Try to transform the material so that you've got on that piece of paper information that's going to help you get 80% of the questions right. And if it doesn't seem like it gets 80% of the questions right, let's see if we can't still improve it. Because it's going to be great if you start the next exam really confident that you've got a big chunk of it already taken care of. If you need my help to make that happen, you're 100% top of my to-do list. Okay, so with that, that's all I got for tonight. I really liked your participation. If you got specific questions, I'll be happy to stick around for it.
Hi, I have a specific question. So I understand how to count the specific pi bonds and sigma bonds when we're given like a Lewis diagram, but I get confused and could use like maybe a refresher, a better explanation of like I'll just read a question that confused me. It was like how, like, to describe the bonds, like in that diagram to the right, like describe the bonds of the hybridization. And because I know it just confuses me.
Is it more like, so I have two different examples right here.
Okay.
The one on the left is saying, tell me how hybridization can be involved with forming the bonds. And the one on the right is saying, tell me about the hybridization, just assign it. Are you able to do the first part, the assigning part?
I'm able to, yeah, I can do like if you're just the assigning, like a single bond is a sigma bond, and then with a double bond, it's one single bond and one pi bond. I can do that.
Got it. So let me add then in sort of our trajectory. The next skill that I would add to that is you need to be able to look at the atoms in the molecule and assign whether they are hybridized or not. Okay, because those hybridized orbitals or not, those are going to what now contribute to those sigma and pi. So the next skill I would have on that is you've got to be able to assign the hybridization. So the way that you do that, any of the atoms that are on the outside, like in this picture, these 4 hydrogen atoms, or on the left picture, the hydrogen and the oxygen, any of the ones on the exterior, you don't have to worry about hybridizing those at all. The ones that you're going to hybridize are all these internal atoms. So on the picture on the right, I see 3 different carbons. They're all going to be hybridized. The one on the left, okay, I see 3 different internal carbons. They're all going to be hybridized. So do you feel like you can identify which of the atoms in the molecule are going to need to be hybridized?
Yes.
Okay, cool. Next thought is you would then look at each of those atoms and you're going to determine the electron domain geometry. So that's going to be accounting for the bonds and the lone pairs. This carbon right here, I see 3 different electron domains. The center carbon, I see 2. And the last carbon, I see 3. I've identified the number of electron domains. How are you on that?
I'm good with that.
Okay, excellent. Then you got just one more part, and the next part's going to be easy. Okay, if something is linear, meaning it has 2 electron domains, that carbon is going to be sp hybridized.
Yeah.
If it has 3 electron domains, it's sp2. And if it has 4 electron domain, it's sp3. So those match up exactly with the electron domain geometry. It's either sp because there's 2, sp2 because there's 3, or sp3 because there's 4.
Yeah.
Okay. So right there, you've been able to, I'd say within this one, identify the hybridization. So this one said, how many of these are sp hybridized? Only the center one is, because only the center one has 2 electron domains. So sort of on your summary sheet, absolutely write that. Absolutely write down electron domain and what it means for hybridization.
Yeah.
Okay. This one right here, then the very last part is how do we begin to put that together? This is about as advanced as you need to get. Notice over here, a sigma bond is being formed.
Yeah.
It's being formed from one carbon atom and the other carbon atom. This carbon atom right here was sp3 hybridized because I see 4 electron domains around it. The one in the center, sp2 hybridized because I see 3 electron domains. Sigma bonds are formed from the overlap of those hybridized orbitals. So it's combining an sp3 with an sp2.
Yeah.
Okay.
I think I understand how to do that, but there were some questions where like we were given what the specific like hybridized orbital looked like, and then it asked like what bonds were present. And it was like,
Yeah. Are you thinking of a, is that on a practice test or mastering chemistry?
it was on a practice test.
Yeah, I've seen that question on mastering chemistry. It's a pretty good question. Now, and when I say that, here I am, I'm a professor saying it's a pretty good question. As a student, you're saying, what the heck are you talking about? What that one is getting at is it wanted to say, okay, is the resulting shape that I see there, is that something that would be accounting for linear? Would it be accounting for trigonoplanar? Would it be accounting for tetrahedral? So it's coming at the same topic that I was just mentioning, how, if it's trigonoplanar, that means it's sp2. What that question did was it showed you a geometry that was like trigonoplanar, and it asked it coming from the other direction.
Yeah. And then I know like there was a lot of questions that had to do with like sp hybrid orbitals. Like when they overlap, they form sigma bonds.
Yep.
And like, how do I distinguish like what's going to form a sigma bond and what's going to form a pi bond?
Great question. So if you're asking me that, that tells me you got a lot of these other parts already.
Yeah.
So if we were to look at this image right here, the one that has carbon, double bond to carbon, double bond to carbon, based on what you just said, you would have said it has a sigma bond and then also a pi bond.
Yeah.
Okay. The sigma bonds are going to be formed by those hybrid orbitals. The sigma bonds are being formed from the sp3 with the sp, because a hybrid orbital, it's constructed so it points directly at its neighbor. Directly at its neighbor means it can form a sigma bond. In order to form a pi bond, it has to be a leftover p orbital. It has to be a leftover unhybridized p orbital. So it's not pointing directly at its neighbor, it's perpendicular to that. So if you want to say, well, how is it put together? Sigma bonds are formed from the hybridized orbitals.
Okay.
Pi bonds are formed from the unhybridized p orbitals that are left over.
Okay. And so like if I were to look at the diagram on the right, I would find the Vesper shapes and stuff, and then I would say, all right, which are going to be hybridized, and those are going to be the sigma bonds, and then I'm going to find where the leftover p orbitals are, and those are going to be facing away from the neighbor.
You got it? And so if I were just to look at that center atom for a second, that's going to be sp hybridized.
Yeah.
There's a total of 3 p orbitals. Sp has taken an S and a P and put it together. So I've got 2 p orbitals left over, right? One can form a pi bond to the left, one can form a pi bond to the right.
Okay, that makes a lot more sense.
Yeah, good question.
Thank you.
Dr. Clark.
I'm sorry.
I'm not sure if you would be able to answer this, but I thought I'd ask. So at the beginning of the year, I knew that every exam that I was going to take was going to conflict with some class. So at the beginning of the semester, so I filed for all 3 makeup exams, and I got like the email like saying what day it would be, which would be next week. But then you said that there could be like a makeup if you have like the in-person lab the day after. So should I take the exam the day after on Thursday, or when they sent me the makeup?
I would take the makeup setup because they already have you in the system for that. I would just stick with that.
Okay, sounds good. Thank you.
Yep.
There was a question on the practice test. It was like, how many electrons are in the pi system of NO3 minus,
Mhm.
and the answer is 6. And it relies on there being, well, I'm just wondering why the oxygens are hybridized instead of just p orbitals being.
How was it phrased? Do you remember?
Yeah, the question is how many electrons are in the pi system of, and it's just NO3 minus, and it's just asking like the delocalized electrons, I think.
Yeah, I think that if I were to say what you're going to be expected or what you might do on that, I think the question that I shared this evening, as far as do you have delocalized or not, I think that's going to be at the level that I would expect. I don't think that the counting of how many would be present, uh, I don't think that's going to be I don't think it's going to be in that format. So if you can say there's delocalized because there's resonance that are appropriate here, I think then you're in good shape.
Okay, and then so you don't think I would need to know that the oxygens are hybridized?
I think that I would say, oh, with nitrate, I see that I have delocalized electrons because I have this fractional pi bond that goes throughout. I think right there, then I'm good to go.
Okay.
Hi, Dr. Clark. I had a question about the, uh, trying to find it, sorry. The bromine fluorine dipole moment being larger than chlorine fluorine, and why one of the explanations is bromine is larger than chlorine. Can you explain that again?
Yeah, so the thing that leads to a larger dipole moment is when the charges, you have a greater positive and negative, and when they're farther apart from each other. And so I think the charges are farther apart if I'm comparing bromine and fluorine, because bromine's a larger atom. So the center of that atom is further away than if they were a smaller one that were together. The way that you sort of do the math on these is when you're considering the charge, when you have a spherical charge, the way the math works, it's as if all of that charge was in the very center of that sphere. And so because bromine's larger, it's going to be further away from the fluorine than compared to the chlorine with the fluorine. So that's making the charge separation greater.
See, that makes sense. Thank you.
There was a question on one of the practice exams that asked us to calculate the charge, the partial charge when there's a dipole moment. It gave us the dipole moment. Do you think that's going to be on the exam?
Now, I think that the two that I have sort of grabbed from this one, I think are the primary skills. Primary skills of being able to judge differences in electronegativity. And then the second being able to describe the factors that contribute to a larger dipole moment. The actual calculation one, I think we've moved away from that. There's not that much value in it because it's a little convoluted to try to actually figure out how to do that calculation. So I think that as test writers, we've decided it's not worth our time to ask that as a long question and only have it be a single question.
Okay, and then there's a lot of questions about like the properties of certain atoms.
Like yeah, I would say, yeah, several of those are all in the grouping of stuff that would be that last quarter of chapter 7, the descriptive chemistry feature there. That aspect on the descriptive chemistry, it's probably no more than 2 questions on the test. So when I'm trying to get, for the masses here, what do I think is the most important features? I'm not spending that much time on it. I would say in your case, I think you're pretty strong on the different sections. So I would treat the end of chapter 7 like I would in a biology class of saying, well, let me read that and have my reading comprehension, see what ideas that I find here.
Okay. And then which section is the stuff about like when elements were discovered and Mendeleev's?
Oh, that's just in the very first page and a half of chapter 7.
Okay, thank you.
Yep.
Do you think on the exam that, like all the practice exams for this one, they had no fill in the answer, like a put in a value? Do you think that's going to be the same?
Well, if I'm trying to think of the questions format wise that might set up for that, I think you could have a Born-Haber one that would set up to fill in the blank. I think you could have one that was sort of like the provided bond enthalpy values. That would be one where you could calculate it. We don't have very many other numbers that we would be inputting. So I would say those would probably be the two examples that I would think. Well, I guess you could also have one maybe where you're asked to calculate the formal charge or calculate the bond order. You know, so it could easily say, oh, enter your value and have it be -2 or something like that. I think the only one category, if I'm a student, where I would put it in and hope for the best would be like a Born-Haber one, right? Because I'd like to see my answer there when I look at it, but it wouldn't matter much to me if you were asking me to input a formal charge or if you're asking me to input bond order or something like that.
Yeah. And then one of the questions on the practice exam says, which of the following steps in the Born-Haber cycle represents the change in enthalpy associated with electron affinity? And just the answers are just delta H2, delta H3, delta H4.
Yeah, I think on that one, on the practice test within that's one that would be paired with an image. I don't know if an image came through on that.
Yeah, there's no image.
Yeah, that's one that would be paired with an image, so it would just be looking to see the correct placement for that. Yeah.
Okay, and that would be different for different ionic compounds, right?
It would be, but like for electron affinity, I'm always looking to the same region of that graph, right? If you give me the image right there, I know that that's always the last step. Is I'm making now the anion. At that point, I have my cation, the anion, and then I'm going to see those come together to form the lattice. So, and I'm also expecting that one to be the electron affinity. It's probably the only step that I have that is exothermic. All the other ones are going up. That's the only one that's coming back down.
Okay. If the standard state of one of the reactants in one of the steps of Born-Haber cycle is like fractional, has a fractional coefficient, do you multiply the enthalpy change by like a half or whatever?
Yeah, correct. And so that's not that infrequent, because a lot of those that we make, it's going to include a diatomic molecule, right? If I got O2, Cl2, F2, all of those in there, the equation, they definitely could have a coefficient of 1/2. And so I would just have to then look to say, okay, if you're giving me data, is that something I need to account for or not? In the one that we had that was given in this other test version I saw, in this case right here, it didn't matter. They were already telling me what the gaps were, and I was just filling in the missing one. It's something I'd have to attend to, though, if you give me the values and you're not really showing me where they show up on the image.
Okay, and the reason you don't need to do it here is because there's already 2 anions in the ionic solid.
Correct. Yep.
Okay.
Correct.
All right. Thank you.
Yep.
See ya.